Hey guys, and welcome back to another tutorial. We're actually going to launch the beginning of Unit 2 this time around. We're going to go over polymers, combination monomers, okay? So, we're going to skip over to page 4, and we're going to talk about just what the word means. So let's break it down real quickly. You've got the word polymers spelled like this, and it's actually split into two different parts. Poly means many, so you guys might have heard this before. Polynumerous, polydactyl, etc., etc. Poly just means many, alright? And mer comes from a Greek word meris. Meris. And what that means is it just means a part of something. Meris is like a part of something. So polymers really just translates to many parts. And that's actually exactly what it means. A polymer is just a bunch of different things connected together. You can think of this kind of like, I think actually on page 3 they gave you a little story about a clock or something like that, but you can think of a car, you can think of anything with different parts. So cars have many parts, clocks have different parts, etc., etc. Alright, so human beings and plants and animals and everything else, they're made up of polymers, or these things that are made up of many different individual parts. So let's go ahead and take a look a little bit more. I'm moving to page 5 now. And it's talking about polymers being the macromolecule of life. Okay, so macromolecules are just going to be another word. Let's go ahead and break that down. So macromolecule. So you guys know what a molecule is. We've gone over this in other tutorials. So that is going to be a combination of a couple elements or whatever like that. And then macro is the opposite of micro. You've probably heard of microchips and micro, I don't know, environments, micro, whatever else. That means small, right? So macro means large. Granted, when you guys hear the word macro, I don't want you to think large like massively big. I want you to think large as in bigger than micro. So microchips and micro whatever, generally you have to use a microscope to look at, or, you know, they're very, very small compared to the other things their size. Macromolecules are just bigger versions of that. So instead of, you know, a virus being a micrometer, or they're actually technically more like nanometers, but whatever. Let's pretend they're micrometers. So as in really, really small, right? You can probably see a macromolecule with a really, really weak telescope. You don't have to have that strong a telescope for that. Okay? So I'm going to go ahead and move on. I'm not sure what page 5 is all about, so I'm going to move on to page 6. So they introduced monomers. Alright, so this is probably where we're going to start. I'm kind of surprised they didn't start with this, but monomers comes from the same two parts, or I'm sorry, with slightly different parts than polymers. That mers still comes from meris, so that means part, right? And mono, you've probably heard of mono. But mono is just going to mean one. It's the opposite of many, right? So this just means one part. Polymers are made up of many individual monomers. Okay, so if monomers are one part and polymers are many parts, you just got to take a bunch of these. So if you take 2 or 3 of these, you got a polymer. Take 100 of these, you got a polymer. Okay, if you have one polymer, you probably have a bunch of these. All good? That's generally the main idea. And they've got a couple examples of monomers here for you, so you're probably going to want to keep that in mind. Glucose, amino acids, and nucleotides. Alright, so I'm going to mark these down. I'm not sure if it's important just yet. Glucose, amino acids, often written down as AAs. I'm going to go ahead and put that in parentheses. I might call them AAs later on. Maybe I'll just say amino acids, just so you guys get used to hearing the words. And nucleotides. You guys actually know what all these are. Glucose is essentially just a sugar. Okay, so if you think sugar, you think glucose. Amino acids are going to be the building blocks of proteins, and nucleotides are your DNA. Okay, so let's go ahead and move on to page 7. Okay, page 7 is going to break down just carbohydrates in general, or sugars. Okay, so I don't know, we're going to go over what a carbohydrate and a sugar is, just so that you guys have a better idea of what you need to know. So let's start over here with glucose. Okay, I don't know if I'm going to fit all this in this column, so we may end up rewriting this a little bit, but it's okay. We can talk about it. It'll be alright. Let's see. So these are called carbohydrates. Or, I'm going to give you another name for them just because I'm not sure how much you'll need. This definitely shows up on your EOC. I don't know if it'll show up on your post-test, but these are also called saccharides. Spelled like that. Alright, so glucose, carbohydrates, saccharides, or you can call them sugars. All of these words mean essentially the same thing. So you just have to get used to seeing all of them and remembering that they're all similar. Okay? So as soon as you see one of these words, what you have to remember is these are energy. That's what they are, okay? So sugars, you know how kids get real hyped when they eat a bunch of fake sugars? Because fake sugars are really easy to break down. So when kids put them in their digestive systems, they metabolize them really quickly and get immediate energy. Now the problem with this energy is that too many of the fake ones especially, so more simple sugars and whatnot. But if you have way too much sugar, you're going to crash eventually because you will break down all that stuff, but you won't have any long-term energy. So these are short-term energy. All right. There's going to be the opposite of that. It's actually not on this page yet. I'll talk about it just in case they don't. The opposite of this, by the way, so you've got sugars, which are short-term energy. Fats are long-term energy, and that's why they take so much energy to break down, and it's really hard to actually lose weight because they're meant for long-term energy. Way back when, that was a really useful thing when you never knew whether or not you're going to have food. So way back when we were, I don't know, hunting animals and that kind of thing, you'd burn up so much energy, and then you'd have to, kill off the animal, you'd have to cook it and skin it and all that jazz. You did a lot of work to get your food. Back then, something like fats and lipids would be really useful because it could stay in your body for a while and you can break it down over time. Sugars, on the other hand, were significantly less useful back then. Now it's kind of the opposite, to be honest with you. Sugars are short-term energy, great for athletes and whatnot, but if you don't use it, they become lipids, they become fats, and fats definitely are hard to break down, especially in current life. Okay, so let's see what else they say about these saccharides or these sugars. Okay, so they don't actually say a whole lot about these. They give you these structural units on top. You'll notice that one glucose is, and I'm not going to draw it out, but essentially one glucose looks like this. Alright. Oh my gosh. Well, mine was ugly, but it's got that same kind of hexagonal form, and that's just a glucose. But if you were to pair a bunch of these up, you end up with something very different, okay? So these are more complex sugars. So this is like a monosaccharide, as in one, a disaccharide, like two, and a trisaccharide, etc., etc. So I couldn't really fit that, but that says tri. I know you guys can't see that, but that's okay. Don't even worry about it. It just means three, right? Like a triangle. So the more of these you get, they have names for all of them. They just get more and more complex with the more and more of these structures. But the idea is you can literally just take the first thing and copy and paste it over and over and over, and you get more complex sugars. Okay? So let's go ahead and move on to page 8. What are they going to talk about? Okay, so page 8 is a question, which is the best definition for a polymer? Remember, a polymer is just a bunch of stuff. So it's a bunch of parts. I like the third answer. A doesn't work because the first answer is a simple molecule. It's not simple. It has many different parts, so that would make it complex. The second one says two molecules held together. It's not just molecules. A molecule does not necessarily make up a polymer. What makes up a polymer is a combination of monomers. Okay, so many monomers equal polymer. Make sure to keep the units straight. Let's go ahead and move on to page 9. So they're showing you linear versus branch polymers. Pretty simply, linear polymers. Let's go ahead and start a new page for this. We might come back to this. I don't really know. But simply put, I'm sorry. Wow, I can't even write properly. Pretend that's an I right there. So linear polymers are just lines. And you'll notice on your picture, just in case you're not looking at it, I'm going to go ahead and draw it. It's just, and they can go up and down. They don't have to be straight lines or whatever. They can be snake-like, but they're just going to be connected in a straight line, all right, linked just together just like that. Branch polymers, on the other hand, you can probably guess, instead of going straight like this, what's going to happen is that you're going to get it to branch out in different ways. Doesn't matter what ways, doesn't matter how many branches. Like I want to have like that many branches or whatever. It's just gonna have lots of branches, right? Different parts. So the idea is this: linear polymers are going to be, they're called backbones. Just like your backbone or your vertebra is a fairly straight line. Like it's a little curve. You should have like an S-shaped curve or something like that, or like a lowercase f. Most people refer to it as an S curve, even though it's not entirely healthy. But we're not going to worry about that right now. It's an anatomy thing. So linear polymers create what's called the backbone because it's got that one line shape. Okay, it does not have to be straight. All right. Now, branch polymers have these, tree-like structures. They're not really called anything. They're just called branches. So the one word I want you to pair with linear is backbone, and the one word I want you to pair with branch is branch. That's kind of easy because that's what they're called. All right. So let's go ahead and move on to page 10. See how far they go. I had a feeling they'd stop because there's actually a lot more to the linear versus branch thing. They actually have very different functions. That's okay. We're just going to move on to covalent bonds and polymerization. All right. So when you put things together, it's called polymerization. So polymerization means to make things polymers. All right, and you make things polymers by connecting them together. So you make things polymers by connecting monomers. Connecting monomers. Okay, and to do this, you uses a covalent bond. Okay, so you use a covalent bond. And if you guys remember from the past tutorials, covalent bonds are shared electrons. All right, so two of the elements within your polymer will just bond together, share their electrons, and that's it. So you end up with a polymer as soon as they form these bonds. All right. Okay, so I don't actually know whether or not this will be all that important, but covalent bonds are different depending on the polymers. I don't know how important this is, so I'm not going to necessarily make you memorize it, but just try to remember that different polymers have different strengths of covalent bonds. That's to say, like, it might be really easy to break down this thing, like, for whatever reason, it might be really easy to break this down. Okay, so there are like a bunch of these. I don't really know why, but let's pretend we have this one structure. Starch has 6 of these, but I'm getting kind of bored of drawing these things. Pretend there are a bunch of these. I don't know. I'm just going to keep going. It's not really structured like this. I just wanted to save room on my page, and there should be probably more of them. But the idea is that there are some of these that are really easy to break down. So these bonds are weak. Like, they're super weak. On the contrary, though, you could easily have another one that's like same amount of things. Actually, not the same amount because then it would be the same thing. But let's say it's like, I don't know, it's a trisaccharide for whatever reason. And this trisaccharide, these happen to be really strong covalent bonds. So you never really know. Each individual sugar, each individual saccharide has their own different type of strength in their bonds. All right. So just remember that they have different strengths. It does not matter whether or not there are a lot of them or a little of them or whatever else. They just randomly, well, not randomly. There's a process for all of that, but you don't have to know the process. But they do have different strength bonds. And that's not all on camera. Let me get all this. There we go. Okay, what type of polymer can be described as having only one? I'm on page 11, by the way, guys. So what type of polymer can be described as having only one starting point and one ending point? Well, take a look at them. Here we've got a starting point, some lines, some dots, some lines, dots, and then an ending point. Here we've got a starting point, a starting point, a starting point, starting point, starting point, and then who knows, they're all also ending points. Not really sure, so this is definitely going to be a linear. Linears have only one starting point and one ending point. Alright, page 12. Now we're going to talk about dehydration and hydrolysis. Alright, so polymerization makes things polymers by connecting monomers. That's absolutely 100% true. Now, there are a couple of other terms that we're going to need you to learn. There's dehydration and hydrolysis. Now, you can probably start to guess what these words mean just by looking at them and breaking them down. When you're dehydrated, that normally means you're thirsty, right? Like the regular kind of thirsty. So this means that you lack water. So you can imagine that dehydration synthesis is probably the removal of water. Hydrolysis, on the other hand, hydro, you've probably heard of it before. Hydro, I don't know, hydroponic. Have you ever grown like an herb garden? Or maybe you played like Pokemon, so like Hydro Blast, Yeah, nerd moments. Alright, so anyway, hydro means water, right? So if this is the dehydration, I told you guys way back in the beginning, generally there's a balanced homeostasis factor and everything. So if there's a dehydration reaction, there's probably going to be a hydrolysis reaction, which instead of lacking water and making you remove water, this is probably adding water or something like that. Alright, so let's go ahead and take a look at what your notes say about it. So on page 12, they say, okay. Yep, dehydration is the covalent bond synthesized by the loss of water. So here you lose water, and that makes a bond. Alright, makes a bond. And here you gain water. So you gain water to break a bond. Break a bond. Alright, so these are two very opposites. Let me get this all on screen properly. No, this probably do be a little bit closer. There we go. Okay, sorry, had to readjust. But so dehydration, you lose water to make a bond. And this creates a covalent bond, like we were talking about earlier. Okay, but you lose water, you make a bond. Hydrolysis is going to be the exact opposite. You're going to gain water and break a bond. Like I said, that homeostasis thing. So if you remember that there's a balance in everything, and you can memorize one of these, I don't know, whichever one makes you happier. You like hydrolysis, you like dehydration, it doesn't really matter. Just pick one that makes you really, really happy, and then just make it the exact opposite. So one loses water and makes a bond. The other one's going to gain water and break a bond. Hydrolysis actually makes a lot of sense. It's kind of like, you guys ever use a water pick? Those things where you have braces, it's easy to clean them out. Maybe you haven't had braces. It's kind of like if I use a really strong fire hose, like a fireman uses with the really, really powerful water, and I blast that at a house. Generally, if that house is like on fire, yes, it puts out the fire, but on top of that, it also kind of breaks the structure of the house. Water, like highly pressurized water, really, really hurts. So that stuff is really good at breaking things, okay? So hydrolysis breaks bonds. Anyway, let's go ahead and move on to page 13 and see if there's anything else useful. Well, actually, we're only halfway through, so these next parts will probably actually be fairly important. Okay, so hopefully you don't have any questions about that. If you do, pause and feel free to message me. We're going to go ahead and move on to page 13. This chapter is going to be a little bit longer, so I know it's been a little while since we've done like a 20-minute, 30-minute tutorial. This one's probably going to be around 30 minutes. Alright, so let's talk about exergonic and endergonic reactions. Eventually, with all these videos, I'm going to be including, I guess, timing tags in the description. Endergonic. Sorry about that. But yeah, I'll be adding timing tabs in the description. So, like, if you're having trouble with just this lesson, I'll be like, well, 1840 exergonic versus endergonic starts, and then you'll be able to go there and we'll talk about it. So, I'll do that after I've done all the tutorials for at least one unit, just because I'm trying to put out all the videos first, and then I'll add the tabs, and then I will try and figure out a better way to present all this to you guys. Anywho, let's go ahead and get on to this. This is going to be pretty easy. We're going to break it down again. So this GON, reaction GON, this generally refers to energy, okay? So this just refers to energy. Exer and ender. Now, some of these words might be a little different from what you're used to, but X comes from EX or EEX from the Latin, which just means out of. So this is outside, alright? So this is when you release energy out of you. So this is to release energy out, okay? Release energy out. These are hot reactions or thermal reactions. So if you ever witness a chemical reaction of some sort, you know it's exergonic because it'll give off heat. It'll be warm. So like generally your teacher, your lab professor, your PA will tell you just don't touch it or be careful because it's hot. Sometimes they don't get that hot, but generally you don't want to touch them anyway. But exergonic reactions release energy, therefore they are hot. Okay, which also means that they will be eventually room temperature, but all of these reactions will eventually get to room temperature. Okay, so endergonic reactions. Let's talk about these. Ender is from the Latin en, which just means, in Greek this means something else, but en means in. Okay, so we're going to talk about the word in. So this means we're going to absorb energy in. So again, that same theme of homeostasis and memorizing two things is going to happen again. One releases energy out, one absorbs energy in. And when you absorb that energy, what happens is that you'll get cold. Okay, so it's going to be the exact opposite. If exergonic or exo reactions release energy and get hot, endergonic reactions are going to absorb energy and get cold. Okay, there are far more exergonic reactions than there are endergonic reactions that we practice in regular life, just because exergonic reactions are generally more exciting. Endergonic reactions absolutely exist, and I'm not going to do any demonstrations right here, just because, honestly, I don't even know why I'm not going to do any. Maybe I will. On the channel, I'll probably start adding experiments every once in a while. I'm going to try and do something later on, and then we'll talk about it. I actually have a good example for an exergonic reaction, so maybe we'll do that. I don't really know. I'd have to go see if I still have all the things for it. But yeah, so exergonic, like I said, are more exciting. Generally, you'll see it. Endergonic reaction, those are less popular, but photosynthesis is actually one. Like I said, they're a lot less exciting. So if I show you a plant in the sun, it's not like you'll see anything being done. You won't be able to feel it getting cold. But endergonic reactions are things like photosynthesis. All right. That's probably the most popular one. Let's see, what else do I have here? It looks like I have a video on page 13 that probably talks about exer versus endergonic. I'm just going to go ahead and move on right now. Oh, here. Cool. So on page 14, they talk about how photosynthesis is an endergonic reaction. I'm going to keep moving on. So, my bad. Release energy and absorb energy, or create energy, really. So what plants do is that in photosynthesis, they take in light energy, they take in, water, and they take in the carbon dioxide that we breathe out, and they create energy out of it in the form of glucose. So they create sugars, right? So that's what an endergonic reaction is. That's why they're a lot less seen. They generally create energy. So this is a lot of plant stuff. So if you've ever seen a plant grow, it's definitely doing these kinds of reactions. Unfortunately, like I said, they're nowhere near as fun to watch. Exergonic reactions are much more exciting, and like I said, I'll probably release a video on one of them soon. Let's take a look at page 15. Okay, so dehydration synthesis. I'm going over the questions this time because I didn't go over the mastery test, so I'm not really sure what's going to show up. So I want to make sure that you guys have these answers. Dehydration synthesis. So we're going to remember dehydration synthesis was where you use water to make things. All right. So dehydration is water to make things. So page 15, which is true of dehydration synthesis. First answer is water molecules are produced as a byproduct. This is actually going to be the right answer because what's happening is you're dehydrating it, right? So that means you end up with water. You end up with some molecule and then water sitting off to the side. So a byproduct just means that you're not using it anymore. And dehydration means we remove the water. Water doesn't just disappear, but it's just kind of hanging out. All right. B is going to be wrong. Water molecules are consumed. They're not consumed because that would be hydrolysis and breaking bonds. So you'll notice that they gave you the definition for hydrolysis. All right, so that's obviously going to be wrong. And then the third answer, water molecules are neutralized. That's not going to happen. Neutralize is kind of a bad word to use in biology. In chemistry, it sort of works. In biology, things aren't just neutralized, they're balanced. They experience homeostasis, so they don't just disappear. All right, so as a general whole, things don't just disappear. All right, so let's talk about page 16. Oh, God, I honestly... So they're going over macromolecules in 16. Okay, I think I'm just going to go over the macromolecules because 17 is the same way. There's some weird exercise in 18. And then they talk about us creating polymers. Okay, so let's go back real quickly and talk about the things I mentioned at the very, very bottom down here. They sort of mention them in a really brief way. I don't know how much of this you'll need to know, but we've already gone over glucose like crazy. So this has been covered ad nauseum. We really don't have to worry about that. Ad nauseum, by the way, very, very good essay word. It's an excellent thing to bring up in conversation if you want to sound smart. Ad nauseum literally means, so I don't know, we're going to put this up here. This is not part of your notes. This is actually not biology related really at all. Ad nauseum. You guys probably know what nausea is. So nausea is just sickness. I don't actually know if this is how you spell nauseum. It's been a while since I've studied Greek and Latin, but this just means sickness. When you're feeling sick, you want to vomit, that kind of thing. And ad means to or toward. So this just means that we've gone over it toward the point of sickness till you've gotten sick of it. It's basically like we've talked about it so much that you're tired and sick of it. It's kind of like when you eat too much of something and then you just vomit. That's where this wordplay comes into play. Anyway, let's go back to actual bio stuff. So amino acids, they're going to be the building blocks of proteins. Building, missed an L in there. Blocks. Got it that time. Of proteins. Alright. And they have a nitrogen base. I'm not going to go too in detail because they didn't go too in detail, so I'm just going to cover the very basics. You are going to see these on your EOC, but I have a feeling that we're going to be covering proteins later on, so I'm not going to worry about it too much. That's amino acids, building blocks, proteins, nitrogen base. Nucleotides are DNA, RNA, so there's genetic material, okay, slash RNA. Is genetic material. And then, it's really unfortunate because I was just going to follow through the notes, but there's actually another one. I'm going to include it here just so I don't have to start a new page. They're going to be lipids. I highly recommend that you guys organize this far better than I've done right now. This is actually super sloppy, but lipids are just fats. Alright, so these are slow energy, long term. Alright, long term. This gives you guys a general knowledge of what these four things are, so I'll keep these on the screen while I talk for a while, just in case you guys need to copy them down. Feel free to pause. I know that I've flown through in all these tutorials in all sorts of different ways, so Page 19 talks about synthetic polymers, so I'm going to leave that on while I talk about this. But synthetic polymers, synthetic just means anything that we make as human beings, alright? So there's synthetic oil, there's synthetic this and that, machines are considered synthetic. If you've ever seen an Android movie or an artificial intelligence movie, those are called synthetic beings or whatever. So it just means man-made. And we've created a lot of polymers as human beings. They make different organic molecules for things like I said, oil for your car. So synthetic oils, we design them in ways that handle high stress. So if you're a racer or whatever, synthetic oils are actually really, really good for your car in order to make it last a little bit longer, a little bit less stress on your engine. On the other hand, if you're a farmer, there are all sorts of synthetic soils, so you can absolutely use cow defecation and chicken matter and whatnot. You can use all those things as fertilizers, no problem. But synthetic fertilizers have been adjusted by human beings to have this much phosphorus and this much sodium and this much whatever else electrolytes that plants need. I don't do a whole lot of farming, so I'm not too good with that one. But and nitrogen. Nitrogen's an important part. So they have these three numbers. They're nitrogen, potassium, and I think phosphorus levels or something like that are differently balanced in a synthetic soil. So those are useful for mankind. Another synthetic polymer that you all are used to, so a man-made thing, is plastic. Plastic is really hard to break down by life because we've developed it that way. It's really bad for the environment, but whatever, we're not all going to live 10,000 years, so I guess we don't care enough. I don't really know. Environment is actually really, really important. For those of you interested, you should definitely study it. Environment is one of the most important studies for human beings, but it's just not my particular area, so I'm not very good at it. So on 20, they talk about the bad things about synthetic polymers. Like I said, plastic can't be broken down very easily. Page 21 asks you a question. Why can synthetic polymers be altered to create so many different kinds of materials? Well, let's take a look at the answers. Let's look at I'm going to start with the second and third one, so you guys can already guess which one I think is right, but whatever. So the second one, they have certain additives to react to form newer materials. Additives. That's weird. It is synthetic, so basically with a synthetic thing, we start with nothing, we take a bunch of things, and we put them together. That means they are all additives. Of course they react to form new materials. That has nothing to do with how easy it is to create different kinds. Like just being able to add a bunch of different things, that's very unusual. Let's talk about the third answer. They have a low molecular weight. No, if we add the right things, it can be really, really heavy. We're not like stuck to just light things. We can create really, really heavy synthetic molecules. All right. Or synthetic polymers, I guess should be what I have to say. Uh, so the first one, they have a hydrocarbon backbone that can be chemically altered. That's absolutely true. So the one thing about synthetic polymers is they all have this hydrocarbon backbone. A hydrocarbon backbone. So I'm going to move off of this. If you guys still need it, feel free to pause here. But yeah, so I'm going to go ahead and use a new page just to cover this real quick. Hydrocarbon backbones really look like this. You guys have actually seen it before. We've talked about it in other. Oh my god, I keep writing on all these desks, and I don't know. I'm sorry. Anyway, hydrocarbon backbones look like this. You guys have seen them before. So here's like, oh, oops. Here's a C bonded to a C, and it's probably got a bunch of other H's attached to it, and an H, and an H, and another C, and then it keeps going. We can create it however long or however short we want. This is going to go, and we can attach different things to this. But the idea is it starts with this base. This is called a hydrocarbon backbone because it has HYD, there's hydrogen, all right, and then hydrocarbon. Can you guess what carbon stands for in this? It stands for carbon, so these C's are that and the H's are that. All right, so that's a hydrocarbon backbone. So let's go ahead and move on to page 22. My computer's taking a sec to load. Sorry about that, guys. All right, so working with polymers. Nope. So this looks like we're just closing out the chapter. It's talking about how we can work with polymers, how we can change them, that kind of thing. And then, yes, you've got your summary here. Okay, so for your mastery test, what I want you guys to note for sure, probably the more important things are, I definitely need you guys to know the difference between exergonic and let me get that on screen, endergonic reaction. So there's that. So this is super important. Okay, you guys are going to have to remember hydrolysis. So let's see if I can't find that real quick. Oh, it's over here. Sorry about that. So sorry about that. So you guys definitely need to know the difference between hydrolysis and dehydration. You need to know both of them. You need to understand how they work and whatnot. You need to know these different macromolecules. So I know this area was really, really sloppy, but properly. Whatever. I'm highlighting this bottom part is really what you guys need to know. So the difference between, by the way, I don't know why I highlighted glucose here. This really shouldn't be. Glucose is a type of all this. This is the main word you guys need to know. I don't know why I underlined glucose. I think it was just like a theme, and glucose was the first word to show up in your tutorial, which is, I don't know. I should have noticed that they're introducing things weird. But so those are called carbohydrates, but you need to know the difference between these. So remember that glucose, short-term energy, carbohydrates are short-term energy and they are sugars. Amino acids are building blocks of proteins, lipids are fats, and nucleotides are your genetic material. Okay, so if you just remember the four of them separately, you should be okay. And then that's it. Honestly, you should be okay. The rest of the questions on the mastery test are all related to, those things, the very basic things. Like, do you know what a polymer is? Do you know the difference between, like, branch and linear? By the way, I didn't say that you need to know this, but you definitely need to know this. Like, if this wasn't obvious enough. So one's a line, so linear is line. You'll see this in math, by the way, too. I'll probably be doing math tutorials eventually, so, I'm going to be mixing things together. Everything's related. And I know I'm talking fast, but this is a summary, so I just wanted to go through quick. We're already at about 34 minutes-ish. So linear means a line. Branch means it has branches, so, lots of ending and start points, that kind of thing. All right. And that's about it that you'll need for this chapter. Let me know if you have any questions, concerns. Sorry I keep moving the papers around. If there's a certain section you need, feel free to skip back to it, pause, copy everything down, do whatever you need. But this should get you through the mastery test. Let me know if you need a hand with anything. And yeah, as always, thanks so much, and sorry for shaking the table. I'll catch you guys next tutorial. Bye.